Okay folks, so in this video I'm going to work a distributed load problem and develop the shear moment diagram from it. So what I've done is I have a beam that's 20 feet long. I have a distributed load here of 7 kips per foot, and then at the other end 5 kips per foot. So I want to develop the shear diagram and the moment diagram for this. I've drawn the shear and moment beam essentially, and then extended my lines down just to help me in constructing this cleanly. So let's begin by talking about the shape of the shear diagram. So any point as I move along the load diagram that I want to find the shear, now that I'm doing, I have a distributed load, I would find the area of that, and that would be the magnitude of my shear. So in this case, the shear diagram will have a shape that comes up from the reaction. It'll be sloping down to some point, and that may be above or below the line, and then it'll come horizontal down more and then back up at the end reaction. The moment diagram will have a shape that's triangular, or sorry, parabolic, so there'll be a curve here, it'll kind of flatten off, and then there'll be a curve up back here. So let's go ahead and solve this. The first thing we need to do is solve for the end reactions, and I'm going to do that on a separate page just so I can keep this a little cleaner as I go. So I'm going to call this, I'm going to draw this reaction in, I'm going to call that L, and this R. So if I sum moments about point L, and I'm just going to go ahead and do the whole thing. Actually, you know what, I think I'll solve this off camera, show you the solution, and then we can get into the shear and moment diagrams. Okay, so I've solved for the reactions. The first thing I did was to convert these two distributed loads into point loads. And then I did the sum of moments about the left side, sum of moments about the right side, and then I did a sum of forces in the vertical direction to check, and my input loads. So 70 plus 25 was 95 kips, and that equaled my reaction sum, so I know my solution's correct. Okay, so let's jump back to this part of the problem, and the first thing I want to do is just write in my reactions here so I have them nice and clean. So the left reaction is 55.63 kips, and the right hand side is 39.38 kips. Okay, so hopefully you can see the approach I use where I take up some space, and what that allows me to do is write it out cleanly and clearly, and not try to solve the whole problem in my head simultaneously, which for my brain just doesn't work. Okay, so let's get back to the shear diagram here. So I'll draw this in pencil just so we can make adjustments as we go. So as I come from right to left, I want to account for every load along that plane or that line. So the first thing I run into is this reaction of 55.63 kips, and that's upwards. So right here, I'm going to come up to 55.63 kips, and just write that in there. Okay, the next thing is this uniformly distributed load will create a triangular reduction in the shear, and the slope will tell me if I cross the line or the horizontal axis before I get to the end. So let's just calculate the shear over here, and that's going to be this shear minus the effect of that. So let's call this 0.2 over here. So V at 2 is 55.63 kips minus 10 feet times a distributed load of 7 kips per foot. So those go away. I'm left with units of kips. And I'll just write it here so it doesn't end up in the way. So that gives me minus 14.34 kips. So that tells me I'm somewhere here. And you don't have to draw it to perfect scale vertically or horizontally. It does help to do it somewhat proportionally. So I'm going to check my number here really quick. So I have 14.34 kips. So I'm going to throw my straight edge on here. That's my shear diagram for this first part of the beam. Okay, now as I continue over, I don't encounter any load from this mark through the 5 foot mark, so that tells me my shear is constant. And then I encounter more shear in the downward direction from here to the end. So let's calculate shear at 0.3. And that's going to be this minus 14.34 minus the effect of this, which is the width times the magnitude. So it's 5 times 5 kips per foot. This is feet. So let me do that. It's 25 minus that, so 30 minus 39.34 kips. So that's going to be out here somewhere. Okay, so that gives me that. Now, as I come to the very end and jump off the beam, I have an upward reaction of 39.38 kips, which here I'm 39.34. That essentially closes me. I'm not going to worry about the rounding error that I carried. And I can see that my shear diagram closes. So it needs to start and close based on the reactions. I could also solve this the other direction. And the only thing that would happen is the shear diagram would flip around the axis. And that would be fine because shear is a shearing force, and if I'm shearing on one side up, I'm shearing down on the other side. So in the end, there's really not positive or negative shear. There's just shear that crosses the line depending on how we're calculating it. Okay, to solve the moment diagram, I need a piece of information here. I need to know the location that the shear crosses to 0 right here. So this dimension here, I'm going to call this the dimension to point X. So the way I do that, excuse me, is to basically say this distributed load at some point it creates enough shear to make this 0. So if I take a relationship of X times this distributed load, that should equal my 55.63 kips. So I'm going to say X times W1 is 55.63 kips. Rewrite this by bringing W1 over. And W1 is 7 kips per foot. Those go away, feet jumps up to the top, and I can solve for X. So it's 7.95 feet. So essentially at 7.95 feet away from the end of the beam, there's been enough distributed load to counteract the reaction. So it essentially says from this point to the left, that load ends up at the reaction here, and this load ends up at that reaction. Okay, so now we're going to look at just a few points on this moment diagram, because going from a triangular or a rectangular load to triangular gives us a parabolic load, and it just gets harder and harder to solve as I go. So let's just look at some discrete points on this. The maximum moment is going to occur where the shear diagram crosses 0. So at this point, up until x, the shear diagram is going to look something like that. And then afterwards, it's going to come down like this. And I don't need to know all of these points, but I do want to know this point that corresponds to x here. Okay, so to get the moment that corresponds to x, it's just the area of the curve of the shear diagram. So let's call this moment of x, and it's going to be 55.63 kips times x, which is 7.95 feet. But because I'm a triangle, I need to get rid of half of that, so I divide by 2. And that's my moment there at the middle. So I get 221.13 kip feet as the moment there. Okay, so now if I want to find the moment here, I can come down here. We'll just call this moment at 10. It's going to be this moment minus the effect of the shear, which is going to bring it down slightly. So I have 221.13 minus the magnitude of 14.34 kips times 10 minus x. So if x, where did that go? X is almost 8 feet. This is 2.05 feet. So I got the 221 in there, 14.34 times 2.05, subtract that at 191.73 kip feet. Okay. This portion here, because the shear diagram is horizontal or uniform, that line would be straight, this would be curved, that would be curved, and that would be curved. Anyway, I can solve for this point by doing a similar thing, subtracting from 191 the effect of this area. So let's do that. Let's call this 0.15. And I'm running a little bit out of room, but I'll just write this right here. I have this moment, because I'm starting at this point, so that always has to show up. Then I'm subtracting the effect of that shear, which is going to be the length times the height. So the area of that is the moment. So I have 14.34 times 5 feet. And rubbing those numbers together, I get 120.03 kip feet. Okay, and then to close this out, to find the moment here, which I know is 0, but to make sure that I can solve it this way as well, I would take the area of the triangle and the area of that rectangle. So let me get another sheet and we'll go ahead and calculate that. So my starting moment is at 0.15. I'm going to say moment at the right end. So my starting moment is 120.03 kip feet. And I'm going to subtract the area of the triangle and the area of the rectangle. So the area of the triangle is going to be, let's see, 39.34 kips minus 14.34. So I'm looking for that height times 5. And then I also want to get the rectangle, so that's going to be a magnitude of 14.34 times 5 as well. Oh, I got to do one thing to this, divide by 2 since I'm a triangle. Alright, so let's crank that out. So 39.34. This should, yeah, that's right. Okay, so I ended up with 14.16, which can't be right because that should be 0. So I'm going to go back through, see what I did wrong, and then come back. Okay, so I traced my error all the way back to the moment at 0.10. So here I have the moment at the peak minus that area, but instead of using the triangle formula, I used a rectangle, so I should have divided that by 2. So I'm going to go ahead and rework that, come back to you in just a sec. Okay, so I found my error. I need to divide by 2 here. That makes that 206. That carries down. 0.15 is 134. And then I come here, 134 minus the area of this, and I get 0.53 kip feet left, which is pretty small rounding error. I really would encourage you not to get too wrapped up in that. One way to know if it matters is to calculate the percent of error. So if I take the percent of error at the compared to the max moment, I have 0.53 over 221 times 100. So I have 0.23% error. That's totally acceptable. Now if you want to take out or go one more decimal point out, go for it, and then that number will be probably 0.03 or 0.02% error. Okay, so just to review the process here, start with your load diagram, calc your reactions, start from left to right or right to left, developing your shear diagram, and that's going to be constant where you have no load, triangular where you have distributed load, and then you take the area of your shear diagram at different points and you can find the moment diagram. So the shear diagram is basically a graphical integral, so you don't have to know calculus, thank goodness. All you need to do is take the area of the shear diagram at any point you care about, and that'll give you any point on the moment diagram. And so let's say I wanted to do this point right here. I would just break that up into 2 parts, a rectangle and a triangle, calc the area of those 2, and that would give me this point right here. Alright, good luck with this, and definitely get in touch if you have problems.